Hi everyone, this is Karthik and welcome to the presentation of the project Simulation and Analysis of Facial Feature Detection using the viola algorithm. And this project has been conducted in EC Department of University of Florida for the course WL6562 Computer Vision and Image Processing under Dr. Depang. Before we start off, I would like to thank Mr. Wu for all the effort he has put into the course and all the knowledge he has showered over us throughout the semester. So let's begin. So today we'll be performing the analysis of face detection using two basic algorithms, one being the Viola-Jones algorithm, the other being the eigenface scheme. So face detection in general is a computer technology that determines the locations and sizes of human faces in digital images. There have been many applications for this, and it's been a mainstream study for quite some time now. It detects facial features and ignores anything else, such as buildings, trees, bodies, and like anything else which can be in the background. It can also be regarded as a specific case of object class detection, uh, which by definition means grouping of different objects of the same class together, which means grouping of, say, eyes. If you take it as a class, we group them together to be one. This here shows a typical example of a face detection algorithm and it's working. So there are many applications, as I've already mentioned. It's been used in biometrics, often as a part of facial recognition systems. It's been used in video surveillance, human computer interface, and image database management. There have been some recent cameras which have started using face detection for things like focusing and photo slideshows, and yeah. Face detection has also gained a lot of interest from telemarketers who used to use for all the various marketing purposes. When we come to different techniques which are used to perform face detection, we come across a few which I'm mentioning here, being principal component analysis, the viola algorithm, edge orientation matching, Hausdorff distance method, and model-based face tracking. Let's talk about eigenface scheme. The eigenface approach began with a search for a low-dimensional representation of face images. Sirovich and Kirby showed that we can use principal component analysis on a collection of faces to form a set of basis features. These basis features, known as the eigenfeatures, could be linearly combined to reconstruct images in the original training set. But in 1991, M. Turk and A. Pentland expanded these results and presented a method called eigenface for facial recognition. It deals with the generation of eigenfaces. So a set of eigenfaces can be generated by performing a mathematical process called principal component analysis on a large set of images depicting different human faces. Eigenfaces can also be considered as a set of standardized face ingredients derived from statistical analysis of many pictures of faces. Any human face can be considered to be a combination of the standard faces. For example, you can say one's face might be composed of average face plus 10%, which generally means that uh, the the degree by which a person's face varies from one of the standard faces for faces utilized in the training set. So the eigenfaces that are created will appear as light and dark areas that are arranged in a specific pattern. This pattern is how different features of a face are singled out to be evaluated and scored. Here we have a few examples of how eigenfaces look like. Like I've mentioned earlier, these are derived from a training set. So a new image which is to be tested is compared with these, and the similarity rating is obtained. And this is the general procedure, the sequence of steps which are used in eigenface detection. The first being the training set preparation. Initially, to prepare a training set, the pictures constituting this training set should all have been taken under the same lighting conditions and must be normalized to have the eyes and mouths aligned across all images. They must also be all resampled to a common pixel resolution, and each image is treated as one vector. Secondly, we have mean subtraction, which means the average image A, which is calculated, is subtracted from the original image in T. Next, we move on to the calculation of eigenvectors, values, and covariance matrix. Each eigenvector has the same dimensionality as the original images, and thus can by itself be seen as an image. The eigenvectors of the covariant matrix are therefore called the eigenfaces. And the last step in this process is the principal component selection. Here, say a d by d covariance matrix will result in d power 2 eigenvectors with each representing a direction in the dimensional image space, and the eigenvectors with the largest associated eigenvalues are kept and the rest are discarded. So as an overview of what we have covered till now, and the advantages of this method are that it is very robust. It demonstrates different ways to extract the eigenvectors based on matrices which are sized by the number of images rather than the number of pixels. But it also has a few disadvantages, which being it requires a very large training set, and the pictures which are used in the training set should all have been taken under the same lighting conditions and must be normalized to have the eyes and mouth aligned across all images, which in general means a lot of effort has to be put into the training set and its constitution. So when we talk about the next algorithm in the presentation, it's the Viola-Jones algorithm. The Viola-Jones object detection framework is the first object detection framework to provide competitive object detection rates in real time, and which was proposed in 2001, by Paul Viola and Michael Jones. Although it can be trained to detect a variety of object classes, it was motivated primarily by the problem of face detection. And it again follows three different steps to achieve its goal. And the first being the feature types and evaluation. And before we move over to that, there's something called a Haar-like feature, which also been discussed. And these will be used in the feature type detection and evaluation in the first step. So these Haar-like features are utilized by the Viola-Jones algorithm, and these are formed by the scalar product of the image and the Haar-like templates. The feature employed by the detection framework involves sum of image pixels within the rectangle radius like these. As such, they bear resemblance to basis Haar basis functions which are already used in image detection traditionally. And the value of any given feature at any given point of time is simply the sum of the pixels within the dark regions and the non-shaded regions in the rectangles. So when we move to the feature extraction, these features are sensitive to vertical and horizontal features, and their feedback is considerably coarser. However, with the use of an image representation called the integral image, rectangular features can be evaluated in constant time, which gives them a considerable speed advantage over their more sophisticated relatives. Because each rectangular area in a feature is always adjacent at least one other rectangle, it follows that any two rectangle features can be computed in a 6-array reference. The next process will be the learning algorithm. The speed with which each features may be evaluated does not adequately compensate for the numbers because they are huge. However, for example, in a standard 24 by 24 pixel subwindow, we have a total of 162,000 possible features, and it is impossibly expensive to evaluate them all. Thus, the object detection framework employs a variant of the learning algorithm called AdaBoost, which selects the best features and trains classifiers that use them. So it's like a chain of people working together, and each person is designed and has been given specific instructions to allow a certain set of values and nothing more. And the last and the most important step of a Viola-Jones algorithm will be the cascading architecture. Here, the strong classifiers, which have been derived from the previous process, can be processed very quickly. But this is not fast enough in terms of real-time simulations. So for this reason, we have very strong classifiers arranged in the cascading order of complexity, where each successive classifier is trained only on those selected samples which pass through the preceding classifiers. And at any stage, if a sub-window is under inspection, has been rejected, then it's never uh, looked upon again. It's completely discarded, and it continues, and the search for the image continues on to the next sub-window. So in essence, the cascading structure therefore has the form of a degenerate tree, like this. Let me say all the here 1, 2, and 3 are the classifiers through which all the sub-windows pass through, and once one of them has been rejected, it's completely discarded, and the next window is worked upon, and the program simulation will be explained now. And this is the code I'll be using to demonstrate the Viola-Jones algorithm, and it basically features two important functions, one being detect faces and one being the object detector. I'll explain one of them in a while now. The first being the detect face parts. It's this is the first stage of the representation process, and we typically have three stages. First being detection of the faces, then detection of the parts of the faces, then building a bounding box across them so as to represent them and to present them in a suitable manner. So here we have the function detect faces, which starts the detector, the build detector, which I'll explain later. And here we see the left, right, and mouse and eye. The other components are being detected through this. And here we have the bounding box procedure, where boxes are drawn across the images which have been found to contain faces in them. And as I've said, the build detector is one of the important components. This is the primary function which is responsible for detecting images, and it depends upon the use of cascade object detector, which is derived from the third phase of Viola Jones in the cascading architecture, and this is freely available in the image processing toolbox which we get with MATLAB. Okay, so let's run this program now. Let's give it some time. It usually takes. Yeah, so there we have it. uh, Here we have is a simulation result of a Viola Jones face detection algorithm, where we see different parts of the face being highlighted using different bounding boxes so as to represent them in a presentable manner. So yeah, and this is a feature detection we get using eigenfaces, where it's only the face which is being detected and not the parts of the faces. And when we move over to Viola Jones, we have the face being detected also with the different parts and features of the face, which is much more desirable. So in results, it's in this we have presented a Viola Jones algorithm which performs better than the eigenface scheme for face detection. The eigenface scheme in general, it suffers with problems like greater complexity and computational time, which are overcome in Viola Jones operation. And Viola Jones also offers facial feature detection, which is more accurate and can be used in many applications. Thank you.